Anybody come up with an idea of at least how to attack that problem? What's the idea?
The volume first to know what the full amount would be.
Find the area of the whole thing.
Area of what whole thing?
Surface area.
Surface area?
Isn't that what it
No,
area
volume.
of distribution?
All right, I haven't heard what I was hoping to hear yet.
Oh, I got it.
What?
You take, well, first of all, you have to set it so that the center of it is going to be the x-axis, and then you're pretty much rotating a circle around x-axis. And so by integrating the area of the circle over the period by integrating it over a period of flow, then you're essentially doing the whole thing that we did with the rectangles, except with circles, over the whole course of the tank.
Okay, I think you're kind of on the right track here because at least you're saying integrate. And I think some of your method is correct in that. I don't think it has to be as difficult as that, though.
I'm just confused.
No, you're on the right track. You're on the right track. Let's first of all agree upon how you'd find the volume of just the cylinder itself. So if someone gives you a cylinder, right, the volume of a cylinder is what? Excuse me. The volume is pi r squared times the height, where the height is this, right? And the radius r is that, right? That's the volume of a cylinder. Do you recognize pi r squared? What's pi r squared? The area of the circle. So isn't the volume of this three-dimensional solid just the area of the surface here, like a cross-section area, times how deep it is? It's like infinitely many circles stacked on each other. So all you do is you find that one area up here, and then you multiply times, find that area, and then multiply times the depth, which is this, right? All right, so on this picture here, we've got our cylinder, our gas tank full of blue gas. Not full, but it's got the blue gas in it, right? Like this. So if I just take a look at that blue part, right? Just the blue part, then it would look something like, I don't know, like that. It's just part of a cylinder, yes? Mm-hmm. And so if I could maybe figure out what the area of that is, would it make sense to you that if I found out that area, then all I'd have to do is multiply by its height, and I should know the volume of that? Yes? So all I need is the area of that front face, this piece right here. If I can find that area, I'm in business, yes? Okay, so why don't we try and do that? So why don't we look at the gas tank from the end, okay, and make it a two-dimensional picture instead of a three-dimensional picture. I'm going to orient the bottom of the gas tank at the x, y axis cross point, so at the origin, right? Got this gas tank's coming in like this, like that, right? It's going up, it's coming around to circle, right? My gas is in here, and that's hitting where here on the y-axis? At 2. Do you agree? At 2 is where that's hitting, right? And so the area that I'm interested in is just this, right? In here. Just what's that area? And that's what we did last class. We tried to find the area between two curves, didn't we? Now there's some symmetry here, isn't there? So I could, if I want, just find the area of that piece and then double it. You want to do that, or you want to do the whole thing? I don't really care. You want to do the half and double it? Okay. So if we're going to do this, if we're going to get this half area right here, there's a couple of things we're going to need to know. First, where do we start our integral at? 0. So our integral should start at 0. Where is it going to end? We don't know. We've got to find where those intersect, don't we? I said where those intersect. That means you have to know this curve, don't you? That means you have to know the equation of a circle and somehow write it as a function of x. So we have to go back now and think about what is the equation of a circle? X squared plus y squared is r squared. That's the equation of a circle that's centered at the origin. Is r centered at the origin? No. Where's the center of our circle? If I draw it like this, where's the center of ours? Right up here at 3, 0, right? That's our center? Because it had a radius of 3, didn't it? You still there? Yeah. So this is the formula if we're at the center. It's correct, but that's not the one we want. We want x minus h squared plus y minus k squared equals r squared. That make more sense? I mean, not make more sense. Does that ring a bell is what I meant to say? Yes? Okay. What's h, what's k? What's hk? Hk is supposed to be the center of the circle, right? So h for us is 0, k for us is 3. So this equation becomes x squared plus y minus 3 squared equals, for us, what's the radius? 3, so 9. Agreed? Now, if I'm going to do this like we did last class, and I'm going to do vertical rectangles like this, and do infinitely many of them between 0 and something here, then I need to be able to rewrite this black curve as a function of x, don't I? To do vertical rectangles, which means you have to be able to solve this for what variable? For y. So can we solve that for y? Let's try. Running out of room here. So if I'm trying to get this in terms of a function of x and solve for y, how about we move the x squared to the other side? Right? And then what? Square root on both sides? Now I'm supposed to do plus or minus, aren't I? Yes? All right, so which one am I going to do, the plus or the minus? Because it can't do both. Let's see. Let's take a look. I'm going to put this, or it could be this. Do you agree? Could be one of those. Which one is it? So what we have to remember is that this is a circle, right? It goes around. And so circles fail the vertical line test to begin with. They're not true functions of x. But when we do this and we get a plus or minus, one of them is the bottom of the circle, the other one is the top of the circle. So there's two halves. That's what this represents. Let me move the 3 to the other side. So we have either y equals root 9 minus x squared, plus 3, or we have y equals negative root 9 minus x squared plus 3, right? Or which one? So which one is it, and tell me why? Bottom one, why?
I think it's going to be the top one.
Top one, why?
Because the slope is going to be positive.
Slope?
Well, the slope is going to have to be positive in order to.
Yes.
I think it's going to be negative. Aren't we working with the bottom half of the circle?
Mm-hmm.
Because we're trying to find the area under that.
So you're thinking the bottom one because it's the bottom half?
Yes.
So use the negative. Well, how about this? Isn't the bottom half have to contain this point? So when I plug in x equals 0, I better get what? 0 for y? Okay, try it in here. If you plug in x equals 0 right there, you get 9. Root 9 is 3. 3 plus 3 is 6. Oh, wait, that's the top of the circle. You see that? You plug 0 in here, you get root 9, negative. That's going to be negative 3 plus 3, that's 0. So this bottom function is the one that's going to generate the bottom part of the circle. Is that fair for you? Okay, so this one's gone. All right. Any questions so far? So now, I'm going to go and try and get where they intersect each other. So I need to do where this blue curve hits the black curve. That means I need to set this function equal to what? 2, right? Y equals 2. So for the intersection, I need to set negative root 9 minus x squared plus 3 equal to 2. Which means I'm going to move the negative root to this side. I'm going to move the 2 to this side. So 1 equals root 9 minus x squared. You all still there? Square both sides. 1 equals 9 minus x squared. X squared equals 8. X equals plus or minus root 8. And I'll do the plus 1. Why am I not going to do the minus 1? It's on the other side, and I'm only going to work on this side, and I'm going to double my answer, right? So root 8, is that good? Okay. So I know where to integrate from, right? 0 to root 8. I just need to now figure out the top function minus the bottom function, right? That's what last class was about. F of x minus g of x, that gives us the area. So integral goes from 0 to root 8 of the top function minus the bottom function d, is it y? Which way is our rectangle? Vertical. Vertical means dx. Horizontal rectangle is dy. So I'm integrating with respect to x. The top function we said was what? The constant 2 function, right? That's the function. This line right here is y equals 2, isn't it? Flat line. So that's the top function. Minus the bottom function, which is, I erased it. I need a little more room. What's the bottom function? Negative root 9 minus x squared plus 3. If we can integrate that, that's the area of that front piece, right? But we're supposed to do what with it? Double it. So twice that will be the area, right? And then what should I do with that to get the volume? Multiply it by the depth of the tank deep that way, which was 12, right? So do y'all want to just stick with area for now and then get the volume later? This is the area, that A, that's what we're looking for. All right, let me try and clean that up a little bit. So the area equals 2 integral 0 to root 8. Because of the symmetry of the problem with that circle, we were looking only from 0 to 8 to get this area, but we said if we want the area of the whole thing, we were going to have to double our answer. So the 2 was just to pick up the other side. What number goes in there? Like I can distribute this, right? So 2 take away 3, negative 1, right? So I have negative 1 in here, and then minus root 9 minus x squared. Dx? Plus, yes. I don't know why I did that. That good? Can we integrate that? I hope so. We spent several weeks on. Antiderivative of 1, of negative 1, is negative x. So the area equals 2 times, let's see, negative x plus, how about this? What's that? Close. If it was 1 over that, it would be. Do we have a formula for something that looks like a squared minus x squared? A formula. It's a trig sub for sure, but is it on our formula sheet? It's formula number, no, it's not 21. No. It's actually formula 30, which is not on your sheets. But do we all understand we could do a trig sub on this? Yes? I'm not going to go through the work. I'm just going to tell you what it is, okay? But I'm using, no, because 21 has plus. Yeah, but 30, which isn't on your sheets, does account for this. So according to formula 30, it's going to be x over 2 square root of 9 minus x squared plus 9 halves arc sine of x over 3, and that's it. And we evaluate that from 0 to root 8. That's it, whatever that is the volume, or is the area of that front face. Yes or no? I don't feel like plugging that in. You just get your calculator out. Root 8 over 2, root 8 squared is 8. Oh, that's nice, right? 9 minus 1, that's going to be 1. Root 8 over 3 arc sine. Ooh, I don't know what that is, but you're going to have to get your calculator out. You're going to get a nice decimal answer here. And that will be the area, right? The volume of the water will be that area times what? The depth, which was, or the height, which was 12. Okay? Can we turn the projector on, Vanessa? Do you mind doing that? Whoa. Seats way down there. Is it coming on? There it is. I'm going to have the computer integrate it for us. So 2 times the lower limit was 0. Square root of 8 is up top. The expression we were integrating was -1 plus the square root of 9 minus x squared. And let me put 2.0. I forgot my parentheses. That didn't take long. Okay, so 8.25, and let's multiply that times 12. 99.0025 cubic feet should be the result. Do you understand? What's the volume of the container? What's the volume of the actual gas tank?
It's 339.
Was it? So the volume of the tank, I'm going to say V of t for the tank, would be pi times the radius squared times 12, which it is what?
339.29.
339.29. That's the volume of the tank itself. What percentage of the tank is full? So take this number and divide it by that number. What would you get? Anyone got it? 29, about 29%, approximately 29% full. So if I had restated the problem and I had said it was 3 feet deep, right, instead of 2 feet deep, you wouldn't do any calculus at all, would you? Right? I mean, that would be obviously halfway. It would be halfway. But because of the curvature of the tank, 2 feet up does not mean that it's, how tall is the tank? 12 feet? Sorry, 6 feet, right? 6 feet. And if we're 2 feet, if we're 2 foot high, right, 2 feet, we are a third of the way up, right, the tank? Are we a third of the way full? Not quite. A third would be what percentage? 33.333. So anyways, okay. That problem was in the book. I'd never seen that problem, and today I just happened to see it. I was like, oh, that looks fun. So I just thought I'd start class with that. That's kind of an interesting problem, though, right? I mean, you can actually apply this to something.
So if you divide the actual tank with the percentage that we got, and then that's how we got the
29. It should have come out to be 0.29, I guess, if you took the 99.0025 and divide it by the 3, whatever you got.
All right.
Yeah. All right, 7.2 today. I don't think there are. I think this is where in the class the notes are going to kind of just be what I do in here. Now I do have some older notes that I wrote that were taken in class that I might be able to give you, but they're not that organized. Yeah. So that means pay attention today and write down things, and I'll really stress if there's something really important that you need to have written down, I'll box it, put stars, and do a cartwheel, all right? All right, so what we're going to talk about now are volumes. That's the title of the section. And this is commonly referred to in Calculus 2 as what we call volumes of solids of revolution. And when we see the word revolution, we're talking about rotation, revolving, not like revolution, like here comes the new revolution, all right? This is just geometrically, we are going to create some solids by revolving things and try and find the volumes, right? That's what we're going to do. So before I can begin, we need to clear some things up. We just established a second ago that if I give you a cylinder, and I turned it on its side, okay, is that all right? Then if I call this distance here h, and then you know this part here is r, then the volume of that was pi r squared h, yes? Doesn't matter that it's sideways now. What if I take a cylinder, and then I take a smaller cylinder, there's the center, and I cut that cylinder out. So let's say that the outer cylinder, the bigger cylinder, has a radius of capital R, and the smaller cylinder has a radius of little r. Then what would the volume of this be? What's that? Volume of big one minus the volume of the little one, right? So the volume of the black one without a hole minus the volume of the red one, which would take out the red one from the big one. Yes? That's simple enough? So it should be, what's the volume of the big one? Pi r, capital R squared, right? Times the height. I didn't label height. That's the volume of the big one, minus pi small r squared height, yes? And they both have pi in them, don't they? So I'm going to pull a pi out. They also both have an h, but I'm not pulling it out the front. I'm going to pull it out the back, and you'll see why, and you'll just have to be patient with me here. So I'm pulling a pi h out, but I'm going to put the h in the back and the pi in the front. And then I'm going to put capital R squared here and minus r squared there. Do you agree that this is the same expression as this? Okay? No problems with that? This right here is what we refer to as a disk. And I know it doesn't look like a disk, but if you imagine a very, very thin cylinder like that, where your h is very small, then we create this thing that looks like a disk, right? You throw it, it's a disk. As opposed to this, which would look like very thin, you've cut something out of it, like, I'm going to exaggerate that cutout like this. We call this a washer. So a lot of times you'll hear instructors talk about this is the method of discs or the method of washers. What I'm about to do, okay? But the idea comes from these two pictures. If you have a solid cylinder with nothing taken out of the middle, it's going to form a disc. If you take a disc and cut out a center from it, which is another cylinder, you create a washer, right? Do y'all see the washer and disc? No questions? All right, let's proceed then. Let's figure out how we're going to find these volumes of solids of revolution. So let's take a very basic function, or let's say two functions. Let's look at the region bounded by the region bounded by y equals, we're going to go really basic here, x, y equals 2 minus x, and x equals 0. Let's take a look at that region bounded by those curves. So I'm going to draw it. Oh, by the way, the video for the solutions for the homework for 7.1 were posted this morning. All right, just so you know. I've started 7.2, but I haven't finished it. Okay. So this is why I brought markers today, because, and I know you don't have markers, and that's not really fair, but since I'm illustrating this, I think the markers will help you. So what I'm going to do is I'm going to start drawing these things, and I'm going to use colors. All right, so let's first start with this graph, y equals x, which is a diagonal like this. Everyone agree? Yeah? Then we have y equals 2 minus x, which is another line. How do I draw it? Okay, so it's negative x, which is this, but shifted up 2. So I have a y-intercept of 2. And then it goes down 1 over 1. So down 1 over 1, it should hit this one. Like that, yes? And then label it y equals 2 minus x. Finally, x equals 0, which is what? The y-axis. So x is 0 is the y-axis. So let's take a look at the region bounded by those three curves. Everyone see it? The region that's bounded by those three? All right, it's this region in here, isn't it? I could ask you right now to give me the area of that, couldn't I? If I asked you to give me the area, you would do vertical rectangles or horizontal? Vertical, right? You'd do vertical because you would have a function on top and a function on bottom. Yeah? But that's not what today is about. What we're going to do now is I'm going to add something to this. We're looking at the region bounded by these. Now, rotate that region about the x-axis. Find the volume of the solid formed. So you actually have to visualize this three-dimensionally. I mean, there's no way I can come over here and just pull this and rotate it and say, there, look at. You actually have to see this. So can everyone imagine that I have this sitting, the whole thing is sitting out here? The x-axis, right? The x-axis is here. Come bring the whole thing out. We've got this little triangle thing right there, right? And we're going to take that triangle and we're going to rotate it around the x-axis until it comes all the way back up. And when I do that, as I rotate, it kind of leaves a trail behind it of triangles, and you get a solid, don't you? And what we want to know is the volume of that solid. Understand? Now I'll try and give you a better picture. Real quick, can we kill the lights? Just real quick. This isn't the same, come on. This isn't the same region that we're looking at right now, but see this right here, this purplish looking thing? Imagine that that's our triangle, right? And we take it and we look at that now, we look at that region, that purple region in three-dimensional space instead of two-dimensional space. Everyone see that? And then take that region and we start wrapping it around the x-axis. When we wrap it around the x-axis, we form this solid. And I can take a bunch of this crap out of here so you can really see it. So there's the solid that I would have had here, right? And what we are interested in is what the volume of that solid is. Later on, we'll also ask what's the surface area. But for now, this is where we start with the volume. Understand? OK. So the way we'll do it, the way we're actually going to construct it and determine the volume is to understand again what the integral meant, right? The integral symbol was a way for us to add up an infinite number of things, right? And what we've been doing is adding up an infinite number of rectangles, the areas, to get a total area, right? Now what we need to do is add up, oops, sorry, let me silence this. We need to add up an infinite number of volumes in order to get a total volume. Same process, just it's going to be a different sort of formula. All right, so let me show you the procedure for this. My drawing's pretty damn good. I'm happy with that. Here's what we'll do. I'm just going to kind of give myself a little space here to the right. So I'm going to erase these. Just kind of erase this a little bit. Since this is our first example, your picture may not be perfect the first time. It's going to take a little while to get used to how to set these up and giving yourself enough room to do all the work. Just bear with me, okay? Just for now. This is y equals that. All right, so here's how I do it. Here's how I recommend you do it. To the right of this, we're going to draw another copy of the x-axis because that's what we're rotating it around, right? And I'm going to draw, this is a curved arrow, a double curved arrow, which represents rotation, right? So this just helps remind me that this is the axis I'm rotating over. Then I'm going to come in here and I'm going to draw an arbitrary rectangle that's vertical in here. So I can do it anywhere, right? I don't recommend you draw it at the edges. Just put it somewhere in the center like we did before. There's my rectangle. Now we know that that rectangle is going to get infinitely thin, and we're going to have an infinite number of them, right? But that's just kind of a general picture. Bring that over, slide it over here to this, keep it off the ground just like it is here. Draw your rectangle just like that. Then come in here and do just kind of a quick label of what the top edge of that rectangle is going to be and what the bottom edge of the rectangle is going to be. So the top edge of that rectangle is always dictated by what function? This top edge, as I move this around, what function determines how high it is? The 2 minus x, right? So up here, the height of this rectangle will always be 2 minus x. Agreed? The bottom edge of this rectangle will always be determined by the red line, which is y equals x. Yes? Now, if I take this sliver, this rectangular sliver, and I wrap it around the x-axis, what would I get? Just that sliver wrapped around the x-axis. What would it create? A washer, wouldn't it? Wouldn't that create a washer if I wrapped it around the x-axis? Do you see it? Because you'll have a hole in the middle, wouldn't you? Imagine I have to take this and I have to wrap it around here. As I come around, I'm going to leave a space in the center, right? So it's going to look, when I wrap it, I'm going to draw the picture of it wrapped below. It's going to look like this. And it will have something cut out of the middle, wouldn't it? So this is a picture of the region. This is a picture of just the rectangle with all the other crap pulled out of it, right? Just the rectangle with what dictates the top and bottom of it. And this is what we call one slice. Okay, one slice of that. Do you know the volume of this slice? You just told me we just had a formula for it, didn't we? The formula that we had, I told you to write it in a certain way, and I said it would look weird, but just bear with me. We said the volume of that slice would be pi. It would be the capital R squared minus the little r squared, and then I told you to leave the h on the outside, didn't I? Okay, so for us, let's start out with what h is. H is this width, isn't it? Well, the height is the width. It's kind of weird, but that's what we're talking about when we say h. For us, what's h? Dx. It's the width of the rectangle, which we know that was represented by dx in our integral, wasn't it? So the width is dx. I'm not going to draw it here. I'm just going to come over here. This width becomes dx. Pi is not going to change. So what we need to do is determine the capital R. Capital R is the distance, right, from the center of rotation to the outer edge, right, of the washer, which if you bring this picture up here, remember our rectangle is actually, if I try and draw the rectangle in here, rectangle is actually in there like this, isn't it? That was that thing that got wrapped around. I don't know if that you can see that, but it's in there. And so we know that the distance from the x-axis to the top of this rectangle is the same as the distance from here to here, which is 2 minus x, isn't it? So the distance from here to here is 2 minus x. And I'm going, from here on out, I'm going to label this as the out. And what I mean by out is that this is the outer radius. If I'm standing here, that's the outer radius. Understand? So like if you're standing there on this axis of rotation and you see this disk around you, this washer, the furthest point out, the outer radius, is that distance from here to here. Yes? Then this distance, right, the little r will be from here to here, won't it? And what's that distance? It's x. It's the red part, x. And from here on out, I'm going to call that in, all right? Out for outer, in for inner. If you want to write outer and inner, you can. So back over here, this formula is going to be the out squared minus the in squared. Do you understand how that's working over here now? Capital R is the outer radius, square it. Little r is the inner. Do y'all see the geometry behind this? I mean, do you see the picture where the formula is all coming from? This is what I was trying to explain to you when we were doing Riemann sums, is that it's important to understand in that integral, the first integral we ever learned, right, that the f of x dx was height of rectangle, width of rectangle. Now, our new integral, every little piece means something in this new integral. The pi comes from the fact that it's the volume of a cylinder. The outer radius comes from the fact that it's a washer, subtracting the inner radius, right? And then this is actually the height of the cylinder formula. Okay, so let's plug this in. This would be pi. The volume of that little slice right here, this slice, will be, what is the out? 2 minus x squared minus the inner, which is x squared dx. That is the volume of this little slice, isn't it? So what do I want to do now? Add them all up. Add them all up. I'd like to take every rectangle that's in here, take infinitely many of them, and create an infinite number of slices and find the volume of all those slices and add them up. And that's what the integral allows me to do. So I'm going to now write down the integral. So keep in mind, this is the volume of one slice. One slice. Okay, the volume of the entire thing, okay, the volume of that entire solid wrapped around will be the integral from where to where? So 0 and then to wherever this is. We never checked, we never figured it out, but it is 1. You would set them equal to each other, or just do a quick visual inspection, right? If I plug 1 in here, I get 1. If I plug 1 in here, I get 1. So they do hit each other at 1. So 0 to 1. And then this, right? Pi can come out of the integral, can it? Then it's the 2 minus x squared minus the x squared dx. There we go. So long as we can integrate that, we've got the volume, which I think this would be a pretty simple integration. I guess since this is my first one, I'll take this one all the way. On the homework, when I'm doing the homework, I think I just set it up. I don't even go the rest of the way. Like on the videos I've done, I just do that and I go, and you can do the rest. All right, so this right here, I would expand this out so I get 4 minus 4x plus x squared. And then I'm going to subtract from that x squared dx. Collect like term. Oh, those cancel, don't they? So it's just 4 minus 4x? That's all I've got to integrate? Why are you so quiet? You don't seem too enthused about this at all. Antiderivative? What's the antiderivative of that? 4x minus 2x squared. Evaluating from 0 to 1. Yeah? Plug in. This is going to be pretty easy to plug in. If we plug in 1, what do we get? 2, right? Plug in 0, we get 0. So it should be pi times 2. So 2 pi. Holy crap. Okay. The volume of the solid would be 2 pi. And then whatever units you're in, you know, feet, meter, it would be cubic feet, cubic meters, whatever the unit is. You don't seem to like this. What's up? Thought y'all would really enjoy this. Okay, I'll try a little harder to impress you, all right? You know where I'm going.
What?
Classic problem.
Plastic rubber?
Oh, I thought you said classic problem. Okay. How about a classic problem? Most instructors don't show their students this, but I'll show it to you because I think it's worth it. All right, so how about this? Because you're worth it? Is that what you said?
Oh, yeah. I was just thinking,
Sphere. What's the volume of a sphere? 4/3 pi r cubed. Says who? Says the formula sheet, right? Says the formula sheet. And where did that come from?
integrating from the area.
Magic. It was magic. How could you come up with an integral that could give you the volume of a sphere? Take the area of what and rotate it around what?
Semicircle.
Semicircle. So what if we take half a circle and rotate it around the x-axis? Wouldn't we get the sphere? Better yet, instead of a semicircle, why don't we just take the first quadrant of a circle and rotate around the x-axis? And then times, actually it would be times 4, right? So look, I'm saying take a full circle, right? This whole circle goes around. Just take the first quadrant of a circle and rotate that around the x-axis, and what would you get? You would get this, wouldn't you? You get half of a circle, and then you just take that answer and multiply it times 2. Did I say 4? I said 4, 2. I'm sorry. Yes, so, yes, rotate that,
This is more sphere.
multiply it times 2. Yeah? Do you think we could do that? Sure. Well, you can do it too, but I'll help you. All right, so if we're going to do this, we need to figure out what the equation of that is, right? Because the region we want to rotate is just that, right? That's what we want to rotate. The rectangle we want to rotate looks like this. And we're going to do a vertical rectangle and just wrap it, right? And then add them all up. Then at the end of that all, multiply by 2 to get the other side. So can we get the equation of this function of x, this red thing? So where's that going to come from? The equation of a circle. Now this circle is centered at the origin, right? So I can use the x squared plus y squared equals r squared. And I'm going to use little r. That way, when we're done, it'll match up with the little r that's here. I'm not telling you what the radius is, am I? Okay. So can you solve this for y? Y squared is r squared minus x squared. Y equals square root of r squared minus x squared. And it's supposed to be plus or minus, right? Is it going to be the plus or the minus on this one? The plus, because it's the value of y, isn't it? And that value of y has to be positive if you're going to be up here. If y was negative, you'd be down here. You'd be on the bottom edge of the circle. So I'm going to take the positive one. Everyone good? That's the function of x up here. R is a constant in this problem, right? R is fixed. All right. X is a variable. R is fixed. So now what I'll do, that I've got that function written down, this is y equals square root of r squared minus x squared, is I will come to the side. I will label my axis of rotation. I will draw my rectangle as it appears to me. And notice that the rectangle always touches the x-axis, doesn't it? Right? That's why it's written that way. What is going to determine the top edge of my rectangle? What determines that? This red curve, right? That red curve is what determines that height. What about the bottom edge? Y equals 0, right? It's never changing, this bottom edge. I better do it in a different color. This bottom edge right here is this bottom edge, and that never changes throughout the entire problem, because as I move this rectangle left and right, that edge stays the same. All right, I know I'm going to rotate this. When I rotate, am I going to get a washer? Am I going to get a disc? Disc, right? There's going to be no hole in it. So I rotate. I'll do it below. Oh, terrible. Like this, right? Get a disc. And so when I have my disc and my axis of rotation here, I just need to get an outer radius and an inner radius. I want you to keep thinking of it that way. The outer and the inner. The outer is the distance from the axis of rotation to this top edge, which is the same as the distance from here to that red. What is that distance? It's actually just the function itself, right? Which is square root of r squared minus x squared. This is the outer one, right? What about the inner edge? It's 0, right? It's always touching. I'm standing at the bottom edge of this rectangle all the time. So the distance from me to it is 0. So this is 0. The 0 is the inner. Yeah? That's all you need to do the integration, to set up the integral. Now, we do need the limits of integration, though. Where are we going to integrate from? 0 to that point, r. It's the radius of the circle, isn't it? So we have it. It's the volume of this. We'll double the answer at the end. The volume of that is what? Integral, before the integral. Pi, okay, pi. And then integral, where to where? 0 to r, right? And then the outer one squared minus the inner one squared. D what for us? Dx, because I oriented my rectangle vertically. The outer was a square root. Sweet. Because when I square it, it's going to go away. I'm very happy about that. You should be too. And then the inner one, which is 0. That's really nice, isn't it? So the volume is pi times the integral from 0 to r of what? R squared minus x squared. That's it, right? Yeah, because that 0 is gone. What is the antiderivative of r squared? Be careful. Oh, careful. R squared x. R squared is a constant. May as well be the number 10. The antiderivative of 10 would be 10x, right? So the antiderivative of r squared is just going to be r squared x. So here's where we are. Pi, antiderivative r squared x, yeah? Now, the antiderivative of negative x squared, yes, that's going to be 1/3 x cubed. So minus 1/3 x cubed. And we're evaluating this from where to where? 0 to r. So let's plug r in. If we plug in r, what do we get? Let's see, pi, and then what? We're plugging in r for what in here? For x. So what's r squared times r? R cubed minus 1/3 r cubed. That's what I get when I plug in r, right? And then I plug in, so I say minus, now plug in 0. It's gone. What's 1 r cubed take away 1/3 r cubed? 2/3 r cubed. So we're getting pi times 2/3 r cubed. Right? Which is the same as 2/3 pi r cubed. And that's our answer. But that's half of it. So you double that answer, and you get 4/3 pi r cubed. If that doesn't get you excited, then nothing is going to get you excited in this class. All right? I mean, we just derived the formula for the volume of a sphere.
Can we derive the formula of a test factor?
Of what?
Like if we tried to take a sphere in 3-dimensional space and rotate that around, would that not be possible?
Well, well, in 3D, take a ball and rotate it around, you'd make like a torus. You'd make like a solid torus. That would be, you could find the volume of that, but that would be a little different than what we're doing here. All right, so hold on. I want to finish this up. This right here is the volume of this, right? Is 2/3 pi r cubed. And so when you bring the other side of it in, you double this answer. 2 times 2/3 pi r cubed is 4/3 pi r cubed. There you go. All right, so it's kind of useful, these solids. I mean, you can kind of come up with some useful stuff if you should ever need the volume of the sphere. See, this is the way mathematics works, though. You know, you use the math as a tool so that you can get yourself to something that people don't have to go through this over and over, right? Like, now you have a general formula for any sphere. You have the volume. Never have to go do that integration again. Okay. How about this one? Let's take, this is another example. We're going to take y equals natural log of x. We're going to take y equals 1, y equals 2, and x equals 0. We're going to take that region. Okay, so this is my region. And I'm going to rotate it about the y-axis. So in all these problems that you're going to do for homework, they're going to give you equations that create the region. They're going to tell you what axis, and when they tell you what axis, it'll say about something. And that about something tells you where you're rotating. All right, so the picture is important. Notice I haven't used a calculator at all. Y equals the natural log of x. So what do we know about natural log of x? Does it have an x-intercept? Where's the x-intercept of natural log? At 1? So how about here? At 1, I know natural log, and let me color code this. Just because it's fun, right? Get to use colors. I get to use colors, you don't. Unless you brought your colored markers, right, Christy? Okay, so natural log, we say dives down like this, and grows like this. I'm not saying you need to go buy colored pencils, okay? If you can do all this with your own, with the, standard lead. You don't have to have the colors. What else do you want to graph here? Y equals 1, where's y equals 1? It's horizontal line. Y equals 1 is a horizontal line. And it goes through y equals 1. So it looks like this. Y equals 2 is another horizontal line above that one, right? And x equals 0 is the y-axis, right? I'm out of colors. That's unless there's a different color in this room. I don't. Oh no. Oh, I have my blue gasoline color. What? Gasoline, not Vaseline. Our problem over there. Some of your classmates were being critical of the blue gasoline. All right, so there we go. Everyone see the region? Everyone see the region? That's our region, right? What is the axis of rotation? The y-axis, not the x-axis. So let me ask you, if we rotated this around the x-axis, we would get a solid, wouldn't we? Can you kind of visualize what it would look like? If this region came around the x-axis. Like a coliseum? Yeah, that kind of laying sideways, right? Like, right? I guess so. It would be like this, but then this would taper in. The inside would go in quite a bit. You would have, if you're looking through it, here's the outside edge. So this comes around, that really doesn't taper properly, but I would be able to put my arm through it, wouldn't I? Because it would have this hole as it came around. And it's kind of more like cut out here, right? Because of this curve right here, it'd be cut out and it would taper to a point here at the edge. These things aren't super easy to visualize, but you do your best. Now, that has a volume, right? That's not the same as the solid I get when I rotate this region around the y-axis, is it? Around the y-axis, do I have a hole in the center of it? No. So around the y-axis, it's going to look more like like this. If I rotate that around the y, it would look like this. I don't know. That's kind of a good enough, I guess, right? This around here, be like a tabletop or something almost. I don't know. Whatever you want to call it. Is that close enough? Do you see it? All right. That has a different volume than the other axis of rotation. So we need to figure out what it is. So what do you see as a potential problem then, if we're going to do it that way around the y-axis? I should also label that axis of rotation. If we're going to go this way, right, and we're going to create washers or disks, then which way do my rectangles need to be facing? Horizontally, don't they? I need my rectangle to look like this, so that when I wrap it around, I create the disk that I need, right? So this is the first time you'll hear me say this. I'll say it several times, though. When you're using the method of disks or washers, okay, which is what we're doing, your rectangle will always be perpendicular to your axis of rotation. This is perpendicular to my axis of rotation. In the last problem, my rectangle was perpendicular to the axis of rotation. There is another method called the method of shells where it's the opposite. Your rectangle will always be parallel to your axis of rotation. So that's what distinguishes the two methods, one we haven't seen. All right, here we go. I'm going to try and transpose this picture below it because my axis of rotation is here. I'm going to bring my axis of rotation down below. I'm going to draw a little rotation. I'm going to bring my rectangle straight down. You may think this is kind of childish to do this drawing, but trust me, it'll help you when we start moving these axes of rotations to different locations. Because we're not always going to use the x-axis and y-axis. We can use basically any line we want. So, what's that? Yeah, so right here, right, this outer one right here is going to be this red curve. And then what about the inside? What about the inner one here? Is this one right here? Yes? So we need to determine, what's it? Okay. We need to determine if we were standing on the axis of rotation, right here, looking out towards our rectangle, which is going to become our disk, what is the outer radius? So what is this distance from here to here? Yes. 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 Which is no and yes at the same time. Natural log of x, correct. Y equals natural log of x, but you can't write it that way. That's right. You've got to solve for x. You have to write it as a function of y instead of x because your rectangle is sideways. Right? Do you agree? Because we're going sideways, the distance from here to here has to be written as a function of y. Right now, the way the problem was presented, this was given to you as y equals natural log x. That would work perfect if it was a vertical rectangle. The height would be natural log x. So how can I get this solved for x? E on both sides? And that gives you e to the y is x, right? So that outer radius is actually what? E to the y. That was a little tricky, right? You have to pay attention to that. What about the inner radius? This was the out. X is 0? Yes. So 0. That's my inner. Nothing else in the formula really changes. You're always going to use that same format. Pi, integral, a to b, you'll have to figure that out. It'll be outer radius squared minus inner radius squared, d, whatever the variable is. I'm going to put this up. Remember I said I'm going to box something and do a cartwheel and all that? I haven't done that yet. I'm going to put something up here in a minute. I'm going to do a cartwheel. Yes. That's good. That's how you'll know that that's important. All right? How about our limits of integration? 1 to 2. So again, we're going different now because we're integrating with respect to y. So our limits of integration have to be our constraints on y. Unfortunately, in this problem, the region is bounded by 1, y equals 1, and y equals 2. So that shouldn't be anything we have to figure out. I'm ready to do it. Let's do it. Here we go. The volume will be pi integral. You said 1 to 2, right? 1 to 2. Outer radius squared. Outer radius, e to the y. So e to the y squared minus, what was the inner radius? 0 squared, and then dy. That's just pi integral 1 to 2 e to the 2y, because we all learned on that test on number 5 that e to the 2y is e to the y squared, right? And can you integrate that? One half e to the 2y. So you have to look at this as being a linear expression inside of the e. So when you integrate it, you have to scale by the a that's in front of the variable. So it's 1 over a e to the 2y. And that's going from 1 to 2. Let's plug in 2. What do you get when you plug in 2 here? Pi over 2 is the same as pi times a half. E to the 4th minus, now plug in 1, pi over 2 e squared. Oh. Yep. It's good enough. We could get that as a decimal, but who cares? Okay. We got 30 minutes still. How are y'all feeling? It's all right? Y'all following this? All right, so let me put the formula that'll be followed by the most impressive cartwheel you've ever seen in your life. You'll be thinking Cirque du Soleil. You'll be thinking, I should be doing something else with my life other than being up here as soon as you see this cartwheel. All right, so the Grandmaster formula, right? For volumes of solids of revolution when we're using discs or what we call washers. It's the same thing. Discs and washers is the same method. The only difference between a disc and a washer is when you do a disc, the inner function is 0. A washer is only created when the inner function is something other than 0, because it cuts out an inside of and it creates the washer. But they both have the same formula. The formula is that the volume will be equal to pi integral a to b of the outer radius squared minus the inner radius squared d what? Could be x, could be y, right? So what do you want me to write? D question mark, okay. And that could be, because that's really what it is. And actually this a and b, those could be limits on x or y. So, it varies. The most important thing for you to understand is that the general formula always has a pi in it. You always have to find the outer radius, and you always have to find the inner radius. If you can determine that from your picture, you're in business. And on your exams, I do want pictures. I want to see you coming up with this formula on your own, because I told you on the test I'm not going to require that you actually evaluate the integral completely. You just have to set the integral up and then just move on. But that means I want detail. Pardon? You don't have to integrate, just set up. It'll just be set up the integral. So here's an idea, here's an example of a problem on a test. Sketch the region, sketch this region, rotate it about the x-axis, now rotate it about the y-axis, now rotate it around this, that, and this. I'll probably have you take one region, rotate it around 5 different things. Each formula will be different. So you have to set up the formula for each one. That's the way a problem would look. All right? Okay, let's try. Let me try to adapt this problem a little bit. Let me do something a little different. How about we take y equals e to the negative x, y equals 1, x equals 2. Take that region and do it about y equals 2. Not the y-axis, not the x-axis, about y equals 2. And I'm really hoping that this problem is going to help illustrate how important it is to draw a good picture. You all ready? Here we go. When I was doing the homework videos for these problems, there was a few where I drew the picture and I realized that my picture was too small, like I needed to focus more attention on one part of the picture. So I just, say in the video, I'm going to erase this and start over because I know now that I've drawn it that I'm going to have to blow it up a little bit to be able to see what I need to see. So be prepared to have to write something over, draw it again. All right, y equals, let's take care of the easy stuff first. Y equals 1, horizontal line, right? Boom, this one right here. Try it, how about here? I'm kind of taking a guess. See, if I were to be like y equals 1 right here, that might be too small. So I'm kind of guessing that my picture's not going to get crazy big and I'm going to be up at 10 or something, right? So y equals 1 is this line right here. What else? I think I'm going to do y equals 1 here. What's next? A vertical, x is 2, so that's right here. And y equals e to the negative x. Nobody wants to see my cartwheel. I thought for sure y'all would be like, where's the cartwheel? I can't do a cartwheel, okay? I've never been able to do a cartwheel. I lied to you. I lied to you. I straight up lied to you. I'm saying it on B. I lied to you. I apologize. I was just trying to get you to anticipate it, that's all. It's for your own good. All right, e to the negative x, what does that look like? It's e to the x flipped over the y-axis. It's the reflection of e to the x. So it looks like, goes up like this. Never hits the x-axis, right? So it comes down and something like that. E to the negative x. Yep. Where am I rotating this around? Y equals 2, which is above this, isn't it? It's above this. It's up here.
Do you have to make a distinction whether you want to rotate it like
Whoever he chooses to rotate.
Ask your question, because I think I should answer it, to make sure. You probably have the same question someone else does. Does it matter?
No, because if you ask to do it about why you're going to rotate it like that, not like that, like you're going to rotate it up.
I'm going to go like this with it, yes?
There's no way you can do it like that because you're not asking that.
I'm not asking about this. If I said y-axis, then yes.
My answer to my question.
Okay, I thought what you were asking, does it matter if you rotate it up and around or back into the board and around? I thought that's what you were asking, but it's the same solid. So, okay, everyone see this? Okay, now to the right. Oh wait, let's draw the region. I didn't even kind of like shade it in. It's this region, right? My rectangles are going to have to be perpendicular to the axis of rotation because that's the only method I know right now, right? But everyone agree that that makes the most sense for your rectangles to be in here like this? Because as you slide this rectangle to the left and slide it to the right, the function on top and bottom are always going to be the same. It's not going to change, right? It'll always be the green on the bottom, the blue on the top as I move that left and right. Okay, so what did I ask you or suggest that you do at this point once you've got all this information down here? Yeah, just do a little separate little transpose your picture over here. And again, I think this is the most valuable part of the whole exercise here. There's that. A rectangle is coming over here, like this. The green is going to be dictating what happens on the bottom. The blue is dictating what's happening on the top, right? The blue happens to never change, right? My axis of rotation is up here. My niece can do cartwheels. And she was in my living room the other day doing cartwheel after cartwheel. She had like 5 different versions of cartwheels she could do, different names for them and stuff. I told her I couldn't do a cartwheel, and she just kept doing them in front of me just to rub it in.
Is that what you want to do? Like you want to do it?
I really do want to do it, but I've never really tried since I was a kid, you know, so I need to. I'm done. I'm past the age limit. There's a certain age. That's it, man. That's it. You need to be going the other way. Start looking for canes.
Didn't
All right.
mean that.
All right. I need to get back to this. I'm losing focus. Everyone okay with this picture? What is it I said you had to look at? The most important part for the integral is to figure out what 2 things? The outer radius and the inner radius, right? The outer radius is the distance from the axis of rotation to the outer edge of the rectangle, right? The axis of rotation is here. The outer edge of the rectangle is actually which part of it? The green part, right? The distance from here to this edge is my outer radius. The distance from here to here is my inner radius. So the distance from here to here, I have to figure out. And the distance from here to here, I have to figure out, right? This is the out, this is the in. But it's not as simple as just, oh, it's that. It's the green function. Because the green function, from the x-axis up to the green function, is the height of the green function, isn't it? So the distance from here to here is what? E to the negative x. That's just here to here. The distance from here to here is what? 2 minus, see, because from the x-axis to here is what? 0 to 2. It's 2, right? So if from here to here is 2, then from here to here is 2, take away the e to the x. So this is 2 minus e to the negative, I said e to the x, e to the negative x is what I meant to say. Do you all see that? That is your outer radius. The inner radius is found the same way, but this time you have to figure out what this distance is first. What's that? That's 1, right? That never changes. The distance from the x-axis up to the blue is 1. So that means the distance from the blue back to here has to be what? 1 also. 2 is the whole distance, 2 minus 1. This will always be 1. And that right there is the inner radius. Any questions?
So for real though, no cartwheel?
No cartwheel. It's not happening. Bless you. We sure? There's no, everyone understands why this is not e to the negative x minus 2. Right? It has to be 2, take away the e to the negative x. All right, I'm ready for integral. As long as we have limits of integration, are we going to have limits of integration? Since we're doing vertical rectangles, it's with respect to x, which means we need limits on x. They are 0 to 2, right? So the volume is pi integral 0 to 2 outer radius squared minus inner radius squared. Don't erase it. It's too late. Dx. Two minus e to the negative x is our outer. The inner is just 1, isn't it? Questions? Dot, dot, dot. So you take that the rest of the way. But that would be the setup of it. On a test, that's what I would want. That setup. All right. Yes?
I'm just trying to find the total volume, but couldn't we also set, like, this is probably not the best way to do it, but you could pretty much skip everything where you're doing the 2 minus e to the x, because essentially the volume, if you rotate around the x-axis, would be the same as the volume rotated around y equals 2. But the thing is, you'd have to sketch it.
Hold on. Let me keep up with your thought here. The volume around the x-axis is the same as the volume around this?
Yeah, of the shaded area.
This region right here.
Yeah,
If I
know it's not
rotate
gonna
it,
work with other ones, but right now.
what do y'all think? Let's see if we all agree with this or not, with Ron or not. If I take this region, let me first make sure I understand what you're saying. If I take this region and rotate it around the x-axis, I'm going to get a volume.
Yeah,
You're saying that's the same as rotating around that one.
yes, but it's not this volume within the shaded area.
Is that what you're saying?
I don't think so.
This instance?
Just think about this. Think about this simple idea. If this goes around the x-axis, how big is the hole between them going to be? Just that big, right? Right? So I barely get my hand in there. It'll open up, but I can barely get my hand there. If I take this around here, how big is that hole going to be? I get both arms in there, right?
It's gonna be a total.
So that's going to be a huge volume that goes through. Make sense? Yes?
If we do rotate it about the x-axis, what is going to be the inner radius?
The inner radius would be e to the negative x. So look, yeah, if you're going around the x-axis instead, which is here, the inner radius would be this distance, which is the green function, which is e to the x. The outer radius would be 1. What I'm going to do now is I want us to do the exact same problem, but I want us to rotate it around y equals negative 2. All right? So instead of having the rotation axis up here, where am I putting it? Down here. And let's see how it changes. So same problem. Same problem, just change it to about y equals negative 2. And since I erased it, and I started to erase it, and you're going to have to redraw it anyway, I'll take the time to redraw it. Dang, man. Y equals 1. Like that. This one came down like that. What was the x? It was 2, right?
Yep.
This was 2. So our region was right in here. This time, though, our axis of rotation is down here. Notice that I'm using a dotted line for the axis of rotation, because that's how I help remind myself it's not the x-axis. That's the x-axis. This is the axis of rotation. My rectangle should still be vertical. And And now I'm going to take that whole picture and transpose it over here to the right side. I like to bring over my axes first. There's the x-axis. I'll even label it x-axis. Over here, my axis of rotation is here. Can y'all see that those are supposed to be like two arrows curling into each other? That's what that is. My rectangles here. The bottom edge of the rectangle is changing as a function of the green one, right? The top edge of the rectangle is never changing, but it's the blue curve that's dictating that, right? Are y'all caught up with me yet on the picture? All ready? All right. Let's have a volunteer for the outer radius. Volunteer. Anyone want to volunteer the outer?
-3 or
Say again?
3?
3. Look at it as an absolute value. Good. So look, we want to know the distance from the axis of rotation to the outer edge. The distance, right? The distance. Distance, we measure that as a positive number. So first we have to go from here to the x-axis, which is what? 2. Positive 2, right? 2 units to get to here. Then we got to go from here to here. From here to here is what? 1, right? Because that blue function is 1, so that's 1. From here to here, as an absolute value, is 2. So the outer radius, the total distance from here to here, would be 3, and that's our out, right? Who wants to volunteer the inner radius?
That's useless.
Go ahead. No? No? What do you want?
2, well, I guess it would be 2 minus e, or 2 plus e.
2 plus e to the negative x. What do y'all think? E to the x minus 2. Well, let's think about it. If you're standing here, what is the distance going to be from here to that edge if you had to walk it, right? So when you walk this, how long is that? How far did you walk there? 2. And then how far do you walk to get to there? E to the negative x. So it's a total distance as opposed to negative 2 plus this much, right? So from here to here is this number. That's our inner. And so the integral becomes integral from 0 to 2 still. That didn't change. Pi. Outer squared. Right? Minus inner squared. Dx. Whatever that is. Where? Positive 2, not negative 2. On here?
Yeah.
Well, remember, the rectangle slides left and right as a function of x, right? And so the x is actually the distance from here to the rectangle, and that x has to vary between 0 and 2. I've got about 10 minutes, so I'm going to just introduce you to this next idea. Y'all good for 10 more minutes? You're going to be all right? We could practice cartwheels for 10 minutes.
I can do like a semi-wheel.
Okay, I want to take y equals x minus x minus 1 squared and y equals 1, and I want to rotate this about the y-axis. got to be kind of quick here because I'm running out of time. Y equals 1. It's the easier one to graph, right? What does x minus 1 squared look like? Parabola, right? Where's the x-intercept? Where does that thing hit the x-axis? At 1? What is the value of that at 0? One, right? What is the value of it at 2? One. Okay, that's what you would get. Again, I don't have time for that, but there's the graph, right? I want to rotate this region bounded by the 2, which I hope you see is this, around where? The y-axis, which is this. What's wrong? Yeah, I'm going to have a horizontal rectangle to do this, right? And what's wrong with using a horizontal rectangle? It's touching the same function. Because the red one is not a function. You cannot rewrite this red one as a function of y because it's the same function. It would fail the vertical line test that way, if that makes sense. So you can't really do it, can you? The method of washers does not work for this. The method of disks does not work for this. But there is a way, and it's called the method of shells, and that's what I want to introduce you to. So keep this in mind as I show you how the method of shells will work, all right? So we're kind of stuck on that. Yeah, I've got enough time. This is really actually kind of cool. All right, don't worry so much about copying this down because the speed at which I'm going to do this, it'll be probably impossible for you to keep up. But you got a video, you can go back and watch it. All right, so check this out. Let's say I have a region like this, and I have something between A and B here that I want to wrap around the y-axis. We can't do it with a horizontal rectangle because of what I just said, right? So this is truly a function of x, but it's impossible to write as a function of y. Here's what I'm going to do instead. Instead of taking a horizontal rectangle and wrapping it around like this, I'm going to take a vertical rectangle and wrap the vertical rectangle around the x-axis. Around the y-axis. What geometric figure would I create if I wrap this? Well, hold on, back up. If I move out to a certain value, let's say x, that's where I draw my rectangle, right? That x varies between A and B. Okay, I take that slice, I wrap it around, what do I get? What does that look like geometrically? A cylinder, but it's hollowed out in the middle, right? It looks like this. Yeah, it looks like this, doesn't it? That's hollowed out in the middle. This thing wrapped around, right, comes around, goes back into the back side of the board and comes back around. I get this shape. Does everyone see that shape? Okay, that is a cylinder, yes, I agree. We can find the volume of that perhaps using a cylinder, but I want to do it a different way. What I want to do is I want to take my imaginary scissors and I want to cut this thing right here, all right? I'm going to take it, I'm going to roll it out, I'm going to lay it flat. So if I lay this thing flat onto the ground, after I've cut it and put it open like that, it'll look like this, won't it? Which is a three-dimensional rectangular shape. It's not a box. We call that a parallelepiped. That's the technical name for it. So we've got this shoebox-looking thing. It's supposed to be taller than that, right? This one looks taller. That's supposed to be the same height, right? So how tall is this right here? How tall is that? Because if I find length, width, and height, I've got the volume of that, don't I? How tall is it? It's just the function. Look, remember, that little rectangle's in there, right? That rectangle was this, wrapped it around. Wasn't that just f? That was just the function's height. That's just f of x. Yes? That's how tall it is. What's the thickness of this thing? It's this thickness, right? Which is dx. So that thickness is dx. And then this is the hardest part of it. How long is this thing? Yep, it's you had your thing here, right? We cut it open, we rolled it out flat. So this length is actually the circumference of the circle right there, isn't it? But the circumference of the circle means we have to know, like if we look at that piece from the top, right? We need to know the distance from there to that edge, which is what? It's just x, right? That was the distance from here to here. That's what created that radius. So the x is kind of like the radius of this thing, isn't it? And so if this is circumference, circumference is 2 pi r, this is actually going to be 2 pi x. And so the volume of that little slab that we've created, the volume of it is those three things multiplied together, which would be what? Give me the constants first. 2 pi. And then how about x, f of x, dx? That would be the volume of that slab. And what do I want to do? Add them all up. And I want to let x vary between where and where? A and b. And this is the formula. Okay, the formula is the volume of this wrapped around the y-axis will be 2 pi, because it's a constant, integral a to b of x times f of x dx. See that? Using this, I never have to actually switch it to a function of y, do I? I can leave it as a function of x and use this formula. So this allows me to get around it. So I think there's something to be said here in my last minute while I'm writing the homework down. Whatever it is that you decide you're going to do with your life, I'm not trying to get too profound here or anything. No matter what it is, the thing that you want to study or do that interests you the most, that you have a passion for, try and understand it more than just know it. Instead of knowing it, just try and understand it more. What's that? 7.2, page 378. I don't know if what I'm saying makes sense, but let me try and illustrate my point. I'm going to turn my video off. But the point I'm trying to make